Okay, finite math students. So as I promised, I'm going to make another video for you that will cover, um, you know, uh, some of these applications of linear programming. Linear programming is actually used a lot in economics, finance, um, banking. Believe it or not, it's used a lot in the airline industry. It's used a lot in operations research, the airline industry. Economists use it when they study, the economies of different societies, different cultures, different governments. So it's actually important. Linear programming is a big deal, and it's considered to be, you know, one of the greatest discoveries of the 20th century. I think it started at the end of World War II. So linear programming, what you're studying in this chapter actually goes back to World War II. Okay, so it has an interesting history. It really does. And is it hard? Well, if it was easy, if college was easy, everyone would have a college degree, right? So it's not supposed to be easy. It's supposed to be challenging. Um, some people only like stuff that's easy. Well, if it's easy, if it's really that easy, then maybe it's not worth doing. So stuff that is hard can be very rewarding. It's hard, but it can be challenging and rewarding, and in the long run, it can be really fun and give you a great sense of achievement and personal satisfaction. Okay? Okay, let me take a drink. Okay, we're going to work on two problems. We're going to work on homework problems 52 and 53. 52 and 53. These are, excuse me, these are application problems. These are application problems, what you call word problems, but really you should call them application problems. Okay? Okay, so number 52, or question 52, problem 52. Let me move this over a little bit. Excuse me. An investor has at most $20,000 to invest in government bonds, mutual funds, and money market funds. The average yields for the government bonds, mutual funds, and money market funds are 5%, 9%, and 2% respectively. So government bonds, the average yield is 5% for government bonds, 9% for mutual funds, and 2% for money market funds. The investor's policy requires that the total amount invested in mutual and money market funds not exceed the amount invested in government bonds. So the investor's policy, let's go over that again. The investor's policy requires that the total amount invested in mutual and money market funds not exceed the amount invested in government bonds. How much should be invested in each type of investment? One second. How much should be invested in each type of investment in order to maximize the return? What is the maximum return in the first year? Okay, so we need to determine what our variables are. So let's say, I'm going to try to write kind of small. So X could be the amount of money that you have invested in government bonds, right? The amount of money that you have invested in government bonds. Y is going to be the amount of money that you have invested in mutual, one second here, mutual funds. Okay. And Z, let's see, Z is going to be the amount of money invested in money market funds. Money market, hold on one second. Money, I'm just going to say money market. Okay, it's money. It's actually money market funds, but here, let me see if I can write that quickly. Okay, I'm actually writing with my trackpad, which is a little bit challenging, but that's okay. So make that look a little better. Okay, so these are the three, my three decision variables in the objective function. So what is my objective function? My objective function is going to be profit is equal to 0.05x plus 0.09y plus 0.02z. Okay. And we know from these problems that, of course, x has to be greater than or equal to 0, y has to be greater than or equal to 0, and z has to be greater than or equal to 0. I think we all agree on that, right? Okay, let me just take a little drink. Okay. It says here, well, you know what, my marker kind of covered it up, but the investor has at most $20,000 to invest in government bonds, mutual funds, and money market funds. It's a little hard to see. Okay, right over here, we can see that the investor has $20,000. Okay, so one of the restrictions is going to be x plus y plus z has to be less than or equal to $20,000. $20,000, okay? And of course, don't forget, x and y and z have to be greater than or equal to 0. That goes without saying. I really should write that down too, right? X and y and z are all greater than or equal to 0, okay? And what's the other restriction? It says here the investor's policy, one second. The investor's policy requires that the total amount invested in mutual and, let me see here, so mutual funds would be Y and money market funds would be Z. The investor's policy requires that the total amount invested in mutual and money market funds not exceed the amount invested in government bonds. So how would we express that as an inequality? Well, y plus z has to be less than or equal to x. Okay. We can change that into this. Minus x plus y plus z is less than or equal to 0. So all I did was I moved the x, excuse me, I moved the x to the other side of the inequality sign, right? I just moved it over here where it becomes a negative x. And that's all there is to it. So this is your linear programming problem. All right, this is your linear programming problem. So let's set up the matrices. Wow, this is getting pretty messy here. Let me just make sure that last one is correct. The investor's policy requires that the total amount invested in mutual and money market funds not exceed the amount invested in government bonds. Yeah, that should be fine. Okay, that should be fine. So matrix, matrix A. Okay, so how am I going to do this? This is so messy, you can't even really see what I'm doing in Mathematica. You know what? I'm going to write this down. I'm going to write this down with pencil and paper, or actually pen and paper. I'm going to write this down because I'm going to have to erase it so that you can see what I'm doing in Mathematica. Okay, so I have, let's see, x plus y plus z is less than or equal to 20,000. And then I have negative x plus y plus z less than or equal to 0. And my objective function is p is equal to 0.05x plus 0.09y plus 0.02z. Okay, so I have it written down on a piece of paper because I need to erase this so that you can see what I'm doing in Mathematica. Okay, there we go. Okay, so let's get started, and I hope you wrote it down as well. I hope you wrote it down as well. Matrix A is equal to 1, 1, 1, negative 1, 1, 1, and then I'm going to convert these to fractions, guys. Instead of using 0.05, 0.09, and 0.02, I'm going to actually convert those to fractions so that we're manipulating exact values in the matrix. I want to evaluate exact values rather than decimal approximations. So that's negative 5 over 100 is the same as negative 0.05, and then negative 9 over 100, and then negative 2 over 100. Okay, and of course, we can see that Mathematica simplified the fractions for me. So you can see that, you know, negative 1 over 20 is the same as negative 5 over 100. Negative 2 over 100 is the same as negative 1 over 50. Okay. Then we have to augment this matrix with the 3 by 3 identity matrix, and that represents our slack variables, and then also the values of the right-hand side. The values, the numbers of the right-hand, in the rightmost column. Okay, in the rightmost column of the linear programming problem. Okay, so join A, identity matrix 3, And that's going to be 20,000, 0, oops, and then 0. And don't forget to put in the number 2, guys, because we're joining matrices. We're not joining linear lists. We're joining two-dimensional lists, which is really what a matrix is. Okay. So then we have to proceed. We have to, figure out what is the solution to the problem, right? Okay, so take a look over here. The most negative value is right over here. We have 20,000 divided by 1, which is 20,000. And we have 0 divided by 1, which is 0. Which is the smallest ratio? 0. So we're going to have to pivot right over here. And luckily, that's already the number 1, which makes things really simple, right? Okay. So there's no need to change row 2 because there's already a 1 in row 2, column 2. So row 1 is going to be row 1 minus row 2. Okay. And then row 3 is going to be row 3 plus 9 over 100 times row 2. Okay, so everything looks good. We're going to have to work on this column right over here. You never pivot. Well, I shouldn't say never. You almost never pivot on a negative number. For these problems that we're working on right now, you do not pivot on a negative number. So you're going to have to pivot over here on the positive 2. Okay. So row 1 contains the positive 2. We're going to multiply that row by 1/2. Okay. Row 2 is simply going to be row 2 plus row 1 because 1 plus negative 1 is 0, which makes perfect sense. And finally, row 3 is equal to row 3 plus 7 over 50 times row 1. Yeah. Okay, and it looks like that's going to be our answer. So what is the answer? How much should be invested in government bonds? Okay. Oops, 1 second, 1 second. This is the government bonds column right over here. $10,000. Okay. And then mutual funds. This is the mutual funds column, right? So $10,000 should be invested in mutual funds. And this is the money market fund column. And it's not a basic column, so by default the value is going to be 0. And this is the maximum return. Okay, so that's going to be $10,000. Mutual funds, $10,000. And this is going to be $0. How much should be invested in money market funds? $0. and the maximum return is going to be $1,400. And there you have it. Okay, there you have it. Okay, so this will be our second and last question for the video. Okay. Clear A. So I'm clearing A because I'm going to store a new matrix in A. Okay. So this is problem number 53. A department store chain has up to $20,000 to spend on television advertising for a sale. All ads will be placed with one television station where a 30-second ad costs $1,000 on daytime TV and is viewed by 14,000 potential customers, $2,000 on primetime TV and is viewed by 24,000 potential customers, and $1,500 on late night TV and is viewed by 18,000 potential customers. Okay, I'm just looking at the numbers quickly. Hold on one second. Okay. The television station will not accept a total of more than 15 ads in all 3 time periods. How many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads? How many potential customers will see the ads? Ignore repeated viewings of the ad by the same potential customer. Include an interpretation of any non-zero slack variables in the optimal solution. Okay, so let me see here. Let me just see how many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads. Television advertising, let me see here. Okay, so what we're maximizing, okay, one second. Right over here, how many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads? So that's actually what we're being asked to maximize, the number of potential customers who will see the ads. Therefore, X is going to represent, one moment. So X is going to represent daytime TV customers. Oh, wait, I don't want to, you know what? I'm going to cover up the problem if I do that. Okay, let me start over. So I'm just going to abbreviate this. So X will be, one second. X will be daytime. This is not easy to write with. Daytime TV. Okay, so then X is going to be daytime TV. Y is going to be primetime TV. Y is going to be primetime TV. Primetime TV. And then Z is going to be late night TV. Late night TV. And actually, I'm abbreviating a lot here to save space on my computer screen. So really, when I say daytime TV, primetime TV, late night TV, what I'm really saying is X is the number of customers viewing the ads on daytime TV. Primetime TV is really the number of customers viewing the ads during primetime TV, and Z is really the number of customers viewing the ads during late night TV. All right. Okay. And it says here how many ads should be placed, how many ads should be placed in each time period. So actually, X is going to be the number of ads placed during daytime TV. Y is the number of ads, hold on one, in order to maximize the number of potential customers who will see the ads. Let me just see what they're asking for exactly. So, okay, right over here, this is really the key question here. How many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads? So this is actually, technically the correct interpretation is X is the number of ads, excuse me, X is the number of ads placed during daytime TV, Y is the number of ads placed during primetime TV, and Z is the number of ads placed during late night TV. How many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads? How many potential customers will see the ads? See, this problem is tricky because there's some ambiguity about what the decision variables are versus the constraints. So right over here, we see this is one of the restrictions. One of the restrictions is you can't spend more than $20,000 on advertising. All right, you cannot spend more than $20,000 on advertising. So if that's the case, and if X and Y and Z are the number of ads that are placed on daytime TV, primetime TV, and late night TV, then we can see that $1,000 for each daytime ad plus $2,000 for each primetime TV ad plus $1,500 for each late night TV ad has to be less than or equal to $20,000. Okay, so that looks good. The interpretation in this problem is a little rough because there's some confusion about whether, the decision variables represent money or the number of ads, but really the key question is how many ads should be placed. So this is really the key question. So really, X, Y, and Z for this problem would represent the number of ads, not the amount of money that's spent. Okay. Let's see. Okay, so the number. Okay, one moment here. The television station will not accept a total of more than 15 ads in all three time periods. So right over there, guys, that's going to be our next restriction. So x plus y plus z, okay, that has to be less than or equal to 15. So yeah, it's the total number of ads. It's not the number of customers. It's the number of ads. So the total number of ads has to be less than or equal to 15. And the money spent on the ads, the total amount of money has to be less than or equal to $20,000. The objective function is going to be, so our objective function here, I guess you would call it, well, it's not exactly profit. Let's call it V for viewing, television viewing. So we have here 14,000 potential customers for daytime TV. That's going to be 14,000 times X. Okay. And 24,000 potential customers for primetime TV. That's 24,000 potential customers for primetime TV. And 18,000 potential customers for late night TV. 18,000 potential customers for late night TV. This is a little hard to read, but okay. So your objective function is going to be V. V is the number of viewers. V would be the number of potential viewers, television viewers. Okay. So you have a potential of 14,000 people who are watching daytime TV, a potential for 24,000 people to view primetime TV, and a potential for 18,000 people to view late night TV. So that's actually going to be, and of course, don't forget, X and Y and Z have to be greater than or equal to 0. So that is our linear programming problem. I'm going to write this down on paper because I'm going to have to erase everything I just drew on the computer, because otherwise you're not going to see, what I'm doing in Mathematica. So I'm going to write this down. You should do the same. V is equal to 14,000 times X plus 24,000 times Y plus 18,000 times Z, subject to the following constraints. And of course, as usual, X, Y, and Z are all greater than or equal to 0. That should go without saying. We have 1,000 X, $1,000 for each daytime TV, plus 2,000 Y, $2,000 spent on each primetime TV ad, plus, oh, I forgot, here, okay, you know what I forgot to write? This is 1,500 times Z, okay, and then plus 1,500 times Z is less than or equal to $20,000. And then we have X plus Y plus Z is less than or equal to 15. Okay, I had to write it down, guys, because I have to erase everything I drew on my computer screen. I have to erase it because otherwise you won't see what I'm doing in Mathematica. Okay, so let's erase this. Okay, A is equal to 1,000, 2,000, 1,500, that's the first row, and then 1, 1, 1 is the second row. And then we're going to have negative 14,000, and then we have negative 24,000, and then we have negative 18,000. And let's see what that looks like. Okay, so this matrix has 3 rows, so we're going to augment it with the 3 by 3 identity matrix. And then don't forget the values in the rightmost column, right? So, join matrix A, identity matrix 3, and then we have 20,000, 15, and of course with most of these problems, guys, the final value, in the lower right of the matrix is 0. And then don't forget the number 2 because we're joining matrices, we're not joining regular linear lists. And then matrix form. Okay, so that looks great. So just to recap, this is your X column, this is your Y column, this is your Z column. This column here corresponds to the first slack variable. This column here corresponds to the second slack variable. This column here you could call V. That represents your objective function and doesn't ever change. And I believe these values, if memory serves, they're actually called resource values. The number in the numbers, the values, the numbers in the rightmost column of the matrix, these are called your resource values. One second here, I'm trying to write this. Resource values. Okay, resource values. Okay. Okay, so let's solve the problem like we usually do. What's your most negative number? You have negative 14,000, negative 24,000, negative 18,000. What's the most negative number? The most negative number is right here, negative 24,000. So we can see that 20,000 divided by 2,000, what is that going to be? That is going to be 10, right? Because 2,000 times 10 is equal to 20,000. Okay, so 20,000 divided by 2,000 is 10, and 15 divided by 1 is 15. Which number is smaller? Well, obviously 15. 15 is smaller than, one second, what am I doing here? Oh, no. Whoa, I have to be careful here. 20,000 divided by 2,000 is 10. Okay, 15 divided by 1 is 15. 10 is smaller than 15, which means this is the stronger restriction. So this is where I have to pivot first. I will pivot right over here on the 2,000. So 20,000 divided by 2,000 is 10. 15 divided by 1 is 15. 10 is the smaller. Therefore, the first restriction is the stricter restriction. So we have to pivot right over here in the first row, second column. Okay? So let's see. Okay, so first row is equal to 1 divided by 2,000 times the first row. Matrix form. And now we want this number here to be a 0. This has to be a 0, right? Okay. So how are we changing the second row of the matrix? Well, 1 minus 1 is 0. So it's going to be the second row minus the first row, and that's going to be the new first row. Okay? And then this value right over here, this has to be a 0. Okay, so we're changing the third row of the matrix plus 24,000 times the first row. Okay, so we're almost done, but we're not quite because there's still a negative number in the bottom row. We have a negative entry in the bottom row. And that negative entry is right over here. So then what's 10 divided by a half? the half is right over here, right? 10 divided by a half is 20, and then 5 divided by a half is 10. 10 is smaller than 20, so we need to pivot right over there. Okay? So we're pivoting in the second row, first column. We're pivoting right here, second row, first column, right over there. Okay? So second row is equal to 2 times the second row. Okay? That 1/2 needs to become a 0. I'm referring to the 1/2 that's right over here. 1 second. Okay. So how am I changing the first row? It's the first row minus 1/2 times the second row. And then finally, I need to get rid of that negative $2,000. It's not, actually I take that, yeah, it is negative 2,000. Actually, it's not dollars. It's not negative $2,000. It's negative 2,000 ads. The correct interpretation would be negative, 1 second, let me concentrate on that. Negative 2,000, actually I think it would be, is it dollars or ads? I think that would be, actually, that would be ads. No, actually it would be dollars. The ads, the number of ads that are placed are right over here in the resource column. So right over here, these values here would actually represent dollars. Yeah, so it is negative $2,000. But right now, don't worry about that. We don't need to know that for these problems. Okay. So, but yeah, the ads that are placed during daytime TV, primetime TV, and late night TV are actually showing up right over here, in the rightmost column. And actually this, you know what, this is the number of potential viewers so far, 240,000. 240,000. So you know what, this is not going to represent a financial value. This would actually be, actually, this is kind of a tricky point. I think this actually, these values, well, this value right here is the number of viewers. This value right here represents the number of viewers so far, which is 240,000. The correct interpretation of these values, that's a little bit tricky. That's going to be a little bit tricky. I think actually that does represent a financial value, but don't worry about it, guys, because for this, for the problems we're doing, right now, it's not really an issue, but it is interesting to think about it. Okay, so finally, in the third row, we would have the third row plus 2,000 times, and in Mathematica, you can just use a space instead of times if you want to. The second row, and that's going to be, okay, so there we have it. So for x has a value of 10, x has a value of 10, y has a value of 5, z has a value of 0. So this is the x column right over here. So we can see x has a value of 10. This is the y column right over here. Y has a value of 5. And the z column is not basic, therefore the z variable has to have a value of 0 by default. And the maximum number of potential viewers of your television ads would be 260,000. So let's see if we got this right. Okay, let's go back to the problem. The maximum number of potential customers who see the ads is going to be 260,000 people. 260,000 people when 10 daytime ads, 5 primetime ads, and 0 late night ads are placed. Check answer. Okay, that is correct. But we're not finished with the problem. Continue. Include an interpretation of any non-zero slack variables in the optimal solution. Okay, so your slack variables are actually going to be right over here. This is S1, and this is going to be S2. Okay, 1 second. So S1 has a value of 0 because the S1 column is not basic. So S1 is equal to 0. S2, okay, this is a non-basic column, so by default, the value has to be 0. Now S2 is the second slack variable, and that corresponds to the second constraint. This has a value of 4,000. This has a value of 4,000. So this goes back to actually what I was pondering a few moments ago, and this is going to answer my question. So let's see if we can figure this out. So let's go back to our original matrix. Our original matrix. Let's see. So the second restriction is right over here. This is the second restriction. It has to do with the total number of ads. But for this problem, okay, one moment. One moment. So this is going to be X. This is going to be Y. This is going to be Z. This is slack variable 1, slack variable 2. This is V, and these are my resource values. Oh, actually, this is why. Okay, this is why I became momentarily confused. Okay, sorry. So S1. Okay, S1 is indeed equal to 0. S1 is indeed equal to 0 because this is not a basic column. But guess what? S2 is not a basic column either. So I had a moment of confusion there. So S2 is not a basic column either. It would be basic. This would be basic if it was like 0, 1, 0 or 1, 0, 0 or, something like that. But, these are not basic solutions. So actually, I don't have any non-zero slack variables. Okay, you have to pardon my moment of confusion there. So there are no non-zero slack variables. Both slack variables for this problem are 0. So what that means is I used up all $20,000 on television advertising, and I used up the maximum of 15 permitted television ads. So let me go over this one more time because there was that moment of confusion where I may have misled someone. Both slack variables are 0 because these are non-basic columns. So this is a basic column. X is a basic column because I see 0, 1, 0. Y is a basic column because I see 1, 0, 0. Z is not a basic column. Where's the single one and the several or multiple zeros? It's not here. S1 and S2 are both non-basic, which means their values are 0. Okay, what that means is I used up all $20,000 on television advertising, and I used up the maximum number of possible ads, which is 15. Nothing is left over. Nothing is left over. So, therefore, we can go back to the problem. Okay, so yeah, this is, it's going to be option D, guys. Okay, I had a moment of confusion. So there are no non-zero slack variables in the optimal solution. There are no non-zero slack variables in the optimal solution. And that is correct. Yeah, so over here, guys, so I almost made a mistake. This is not the value for S2. If S2 had a non-zero value, it would be read from the right-hand side of the matrix, not the bottom row of the matrix. So, but we can see that S1 is not a basic variable, and S2 is not a basic variable. Therefore, we know that S1 is 0, and we know that S2 has to be 0. Okay, so we see then that there are no non-zero slack variables in the optimal solution, which means we used up all of our original resources. We used up the whole thing. Okay, all right, that's it for today, and hopefully this video will help you with your homework, okay? All right, everyone, take care, and have a wonderful rest of your day. Okay, bye-bye.